Welcome, my name is Barry Setterfield. On the 21st of August in 2017, we saw a total solar eclipse. This is not unusual in itself, in fact it's quite predictable. Once every 18 months or so we get a total solar eclipse. But what was different this time was that it was seen across the whole of the United States of America. What happens at times like this is that the moon comes between the Earth and the Sun. And what is important here is the relative size, and this is the key. The moon is much closer to the Earth than the Sun, but its relative size is such that at the Sun's distance, the moon can just block out the light coming from the Sun. And when this happens, at totality, we see the atmospheric layers around the Sun, called the corona. So let's start by looking at the Sun's layers. Here are the different outside layers of the Sun. The photosphere is the outside of the Sun that we see every day. But when it is blocked by the moon, we can see the corona, the atmosphere of the Sun, as shown here. How can our tiny moon block out the Sun? If you hold up your thumb and look past it, you can block out an entire tree, or maybe even a mountain. Distance is a clue much more than the size. Our moon is 400 times smaller than the Sun, but it is also 400 times closer to us. So it's the perfect size and at the perfect distance to give us a total solar eclipse when it passes between the Sun and us. If you were in a place where you could see the total eclipse, or if you saw it on TV, what you did see is the Sun's atmosphere, the corona. But there are a couple of things about the corona which really puzzle astronomers. First of all, here is a standard model of the Sun, which regular astronomy believes is a nuclear furnace in its core. This means that what is expected is that the hottest part of the Sun would be in its centre, with temperatures cooling a bit the further away from the core that you get. But that is not what happens. Look at what astronomers have found. The photosphere of the Sun is pretty hot. It's about 6,000 degrees Celsius or centigrade. Then the temperature goes down a bit at the lower chromosphere to 4,000 degrees. The chromosphere is the lowest part of the Sun's atmosphere. But then the temperature climbs to 10,000 degrees. And as if that were not puzzle enough, in the corona itself, the temperature hits an unbelievable 1 million degrees Celsius. At times it can go over 2 million degrees. That has been a mystery to astronomers ever since they discovered that this is what's happening. Here's what Dr. Brooks, an astronomer from George Mason University, had to say about the results of his team's research published in the journal Nature for August 2017. Quote, "Why the Sun's corona is so hot is a long-standing puzzle. It's as if a flame were coming out of an ice cube. It doesn't make any sense. Solar astronomers think that the key lies in the magnetic field, but there's still arguments about the details." End quote. But there is another puzzle too. Our atmosphere on Earth is mostly nitrogen, which is heavier than hydrogen, but still a light element. In our atmosphere, the nitrogen is mixed with oxygen and a few other light elements that make up what we breathe. We do not expect things like iron to be in our atmosphere. Iron is heavy. It sinks to the ground here on Earth. We know that the key element in the Sun's atmosphere, the corona, is hydrogen. In other words, the Sun's atmosphere is mostly hydrogen, the very lightest element. We are much smaller than the Sun, so our gravity is less. Iron sinks to the Earth here. But in the Sun's atmosphere, scientists have found heavy elements like iron. What is iron doing there up in the Sun's atmosphere? The green in this image is the light emitted by the element iron, and you can see it in the corona. Photos like this show the element's colours when seen through a special instrument called a spectrometer. Dr. Brooks' team concluded in the same article mentioned above that, and I quote, "An unknown mechanism preferentially transports certain elements such as iron into the corona instead of others, giving the corona its own distinctive elemental signature." End quote. Here is another anomaly, which indicates the current standard model of the Sun might be wrong. Sunspots on the Sun's surface appear at intervals. Sometimes there are a lot of them and sometimes not so many. The number of spots varies over an 11-year cycle. A closer look shows us that these spots dip deeper down into the Sun from its surface. If the Sun were actually a nuclear furnace in its core, then these sunspots should show higher temperatures since they go down lower into the Sun. But the temperature does not behave as expected. The surface or photosphere of the Sun has a temperature around 6,000 degrees C, while the centres of the sunspots range from 3,000 to 4,000 degrees. Let's add one more problem that standard astronomy has with the Sun. It shoots out a stream of particles that we call the solar wind. These are positively charged particles, mainly just protons or hydrogen nuclei, if you like. If we were not protected by our plasmasphere or magnetosphere, of which the ionosphere is the lowest layer, the solar wind would destroy us. This diagram shows the size of the plasmasphere compared to the Earth, and shows it generally has the shape like a windsock, with a snub nose pointed towards the Sun. It has a long tail streaming out in the direction away from the Sun. This tail moves to and fro in the solar wind. On Earth, if we shoot a rubber band or even a bullet, the object that has been shot out will gradually slow down. This is also what we would expect with the solar wind. We would expect it to slow down the further away from the Sun it was. But that is not what happens. The solar wind speeds up the further out from the Sun it goes. Its speed as it passes Mercury is much slower than its speed as it passes the outer planets and goes on towards the Kuiper belt. So why is it speeding up? Solar winds leave the Sun at between 250 and 400 kilometers per second. At the Earth, the solar wind speed is about 470 kilometers per second. The Ulysses spacecraft measured these same winds at Jupiter as going from at least 600 to over 900 kilometers per second. Now, standard astronomy has trouble with a number of other matters, as well as the Sun. But in this case, we're talking about the Sun, and there are 4 things which are important here. First of all, there's the incredible heat which is there in the Sun's corona. Secondly, iron is found in the Sun's atmosphere. That's the element iron. Thirdly, there are sunspots which are very much cooler than the rest of the surface of the Sun. And fourthly, there is the solar wind which speeds up the further away from the Sun it goes. Standard physics and gravitational astronomy have really struggled to find answers to these puzzles. In contrast, plasma physics gives simple answers with no extra assumptions. So let's look at what this is all about. What is plasma physics? Simply, it is the study of how plasma acts. This is not plasma in your blood. The plasma we are talking about is the 4th state of matter. Plasma is formed when electrons dissociate from their atom and are wandering freely. The atoms are said to be ionized when this happens. The nucleus is the ion, and the electrons are on their own. We know solids, liquids and gases. In solids, the atoms and molecules are tightly packed and usually in specific arrays. At a certain heating point for each solid, it will become liquid. This is when the atoms and molecules are bouncing off each other to the extent that the solid loses its shape and melts. The bonds are between the molecules and they're weakened. Heat a liquid even more, and the atoms and molecules are hitting each other at such a rate and with such a force that there is even more space between them, and that is a gas. The bonds between the molecules are now non-existent. We see this easily with water. Solid ice, then liquid water, then gaseous steam, as the temperature rises and the bond strengths lessen. But if the temperature is increased enormously, or if electrical charges are added, or both, one or more electrons are released from the atoms. This then leaves us with a lot of positively charged ions and negatively charged loose electrons. This is a plasma. Once those ions start moving, and once those electrons start moving, we have electric currents. Every electric current is surrounded by a confining, circling magnetic field. This is called electromagnetism, and it is a very, very strong force. Gravity is a weak force. You defy it every time you pick up something. But electromagnetism is very much stronger. Out in space, it can be up to 10 to the 39 times stronger than gravity. That is the numeral 1, followed by 39 zeros. Through the years, astronomers have begun to discover that almost everything we see out in space is a plasma. Radio telescopes have found exceedingly strong magnetic fields coming from enormous electric currents flowing in filamentary clouds of gas and dust. In addition, astronomers have been able to discern temperatures of some gases that range up to millions of degrees. Standard astronomy states that stars form as a result of the gravitational collapse of their gas and dust particles. All by itself, there are some major problems with this theory, because the closer the atoms and molecules get, the more they hit each other and thus force each other apart again. And gravity is a weak force compared to the electromagnetism, which is also present. But in plasma filaments, a different process operates. Instabilities in temperature or electric current flow in a filament in the lab, on the top left image, will cause the circling magnetic field to pinch, twist or kink the plasma. It also happens in outer space. There we see stars which have formed at the pinches of giant plasma filaments, like the Ant Nebula at the bottom left and the Butterfly Nebula on the right. There are many other examples out there. When we look at the spiral galaxies, we see the stars have formed along the plasma filaments making up their arms. They look like beads on a string. We see that in this example of the galaxy M81, imaged in infrared light to show where the stars are by their heat. In our own galaxy, we can see stars forming in large numbers on plasma filaments in the constellation of Orion. This is one of many locations where this process has been documented. In fact, the European Space Agency news release for the 1st of June 2015 states that the whole of our Milky Way galaxy is made up of filamentary structures. We know from the laboratory and playing with plasma balls that plasma filaments can be very unstable. We can also see this easily with lightning, which is a plasma filament. We can see this when we play with a plasma ball as shown here. Just about anything can disturb a plasma filament. They pinch easily. With lightning or the plasma ball, the effects are very short term, as negative and positive charges rapidly seek to cancel out each other. But out in space, the plasma filaments are not only thousands and even millions of times larger and longer, they are there for the long haul, and we can study them. Suppose the Sun, being a star, is not a nuclear furnace, but a plasma ball. That alone would answer the first three problems mentioned here. It answers them immediately and easily. Let's look at the solar wind first. To introduce this, see how opposite charges attract. In this diagram, the positive charges are blue, while the negative charges are red. The red negative charges are attracted to the blue positive plates. Conversely, the blue positive charges are attracted to the red negative plates. This can be demonstrated in the lab. Out in space, our Sun is a star, and many other stars are seen forming as a result of pinches in large plasma filaments, just like the one shown here. In such plasma filaments, something else also happens. A sorting of elements occurs in a way that is dependent on the ease with which an electron can be stripped off its atom. This process is called Markland Convection. This sorting leads to strong positive charges in the centres of the plasma filaments, where the star is, while the outside of these filaments is more negatively charged. Our Sun and solar system are the same. The point that is important here is that there is a good reason why the outer reaches of our solar system are more negatively charged than the Sun. It is for this reason the solar wind speeds up as it passes the various planets. The positively charged protons emitted by the Sun are attracted strongly to the negatively charged outer areas of our solar system the closer they get. This is going to be important in discussing the next point. Second, the extremely high temperatures of the Sun's corona have to do with the solar wind. Now consider this. If the Sun is in reality a plasma ball, then the core will probably not be a nuclear furnace. Instead, it can be shown that nuclear fusion reactions will occur on and near the surface, in a way typical of some arc mode plasmas. The main point is, however, that the heating in the solar corona occurs as particles of the solar wind are accelerated away from the Sun's surface. As they stream away from that surface with increasing velocity, they collide with neutral atoms and other ions in the Sun's atmosphere, which, by comparison, are almost stationary. These collisions result in a huge amount of turbulence, and this turbulence results in the enormous temperatures that we see in the corona. To get a picture of what is happening, think of a waterfall or a cascade over a dam wall. The water accelerates due to gravity this time as it goes down the fall. Then it hits the stationary water at the bottom, and there's a great deal of turbulence. A smoothly flowing river demonstrates the same idea when it hits a lot of rocks and boulders forming rapids. The Sun's outer atmosphere is relatively stable, but the solar wind hitting it causes the turbulence. Turbulence means atoms and ions hitting each other hard in rapid and random motion, and this results in heat. In the case of the Sun, this results in an enormous amount of heat. Our third point concerns the concentration of the element iron in the corona, and it is not the only heavy element found there. Why are these high concentrations of heavy elements found in the outer atmosphere of the Sun? Standard astronomy considers the core of the Sun to be a nuclear furnace, in which nuclear fusion produces heavy elements. There is no explanation, therefore, as to why these elements, which are said to form in the core of the Sun, should be in such large concentrations in the corona. But if the Sun is a plasma ball, the nuclear fusion reactions are not going on in the core, but on or near the surface. Therefore these heavy elements are there on the surface initially, where they have been formed. Consider a proton, the nucleus of a hydrogen atom, being accelerated away from the Sun by a strong negative charge, such as exists in the outer solar system. The proton is being attracted by the more negative force, but that is just one proton. Now consider the clump of protons in a heavy metal such as iron. There are 26 such protons bound together. They will be the more strongly attracted by that outside negative charge and will thus respond accordingly, flying up into the corona. This easily explains why we see evidence of so much iron and other heavy elements in the Sun's corona or atmosphere. Finally, consider the sunspot question. It becomes almost moot. If the Sun is not a nuclear reactor in its core, there is no reason that sunspots need to be hotter as they go down into the Sun. In fact, there is every reason for them to show somewhat cooler temperatures as they go down away from the nuclear fusion taking place on the surface. Plasma physics is not yet widely accepted by most astronomers. Gravity has been considered the major factor influencing our universe. But again, gravity is a very weak force. It is when one considers electromagnetism and plasma physics that so many answers appear to be so readily available. So to conclude, when you recall the eclipse or see photos about this eclipse or other eclipse, remember you're seeing the corona. That's the incredibly hot atmosphere of the Sun, which contains heavy elements. Also, you can see the start of the solar wind. Standard astronomy has trouble with these and other data. Remember, plasma astronomy has possible answers to these puzzles. We hope you enjoyed the eclipse, and we thank you for giving your time here now.